Good day everyone, I am Rizame Siripolio, your reporter for Lesson 3, which is Spanning Sets and Linear Independence. But before I proceed, allow me to read the learning outcomes for this lesson. At the end of the lesson, students will be able to write a linear combination of a set of vectors in a vector space V. Secondly, determine whether a set S of vectors in a vector space V is a spanning set of V. And lastly, determine whether a set of vectors in a vector space V is linearly independent. So let's define linear combination of vectors. A vector V in a vector space V is a linear combination of the vectors u sub 1, u sub 2, all the way through u sub k in V, when vector V can be written in the form V equals c sub 1 u sub 1 plus c sub 2 u sub 2 plus all the way through c sub k u sub k, where c sub 1, c sub 2, all the way through c sub k are scalars. For example, letter A, for the set of vectors in R3, S equals 1, 3, 1, 0, 1, 2, and 1, 0, and negative 5, where V sub 1 is a linear combination of V sub 2 and V sub 3, because V sub 1 equals 3, V sub 2 plus V sub 3 equals 3 times 0, 1, 2 plus 1, 0, and negative 5, which is equals to 1, 3, 1, which is the V sub 1. Letter B, for the set of vectors M sub 2 and 2, S equals 0, 8, 2, 1, 0, 2, 1, 0, 1, negative 1, 3, 1, 2, and negative 2, 0, and 3, 3. Where V sub 1 is a linear combination of V sub 2, V sub 3, and V sub 4, because V sub 1 equals V sub 2 plus 2 V sub 3 minus V sub 4. So, the answer for that is 0, 8, 2, 1, which is the V sub 1. In this example, it is relatively easy to verify that one of the vectors in the set S is a linear combination of the other vectors because the coefficients to form the linear combination are given. Another example, write the vector W equals 1, 1, and 1 as a linear combination of vectors in the set S 1, 2, 3, 0, 1, 2, and negative 1, 0, 1. So, solution, we need to find the scalar c sub 1, c sub 2, and c sub 3. Then, follow na to itong formula nga c sub 1, u sub 1, plus c sub 2, u sub 2, plus c sub 3, u sub 3, which is may equal siya sa 1, 1, and 1. So, distribute, we have c sub 1, 2, c sub 1, 3, c sub 1, plus 0, c sub 2, 2, c sub 2, plus negative c sub 3, 0, and c sub 3. Next, proceed ta atong vector addition. Then, we have c sub 1 minus c sub 3, comma, 2c sub 1 plus c sub 2, comma, 3c sub 1 plus 2c sub 2 plus c sub 3. And then, equating corresponding components yields the system of linear equation. So, kung ano to tong 1, 1, and 1, which is vector W as a linear combination. So, c sub 1 minus c sub 3 equals 1, 2c sub 1 plus c sub 2 equals 1, and 3c sub 1 plus 2c sub 2 plus c sub 3, which is equal to 1. And then, magamit ta og Gauss-Jordan elimination, which is na tackle na to in the previous lessons. Then the augmented matrix of the system row reduces to 1, 0, 0, 0, 1, 0, negative 1, 2, 0, 1, negative 1, and 0. So, kani siya nga system na siya infinitely many solutions. Each of the form c sub 1 equals 1 plus t, c sub 2 equals negative 1 minus 2t, c sub 3 equals t. And then, para ma-obtain na to, isa ka solution, we could let t equals 1 Then, C sub 3 equals 1. C sub 2 equals negative 3. C sub 1 equals 2. And we have vector W equals 2V sub 1 minus 3V sub 2 plus V sub 3. So now, let's define spanning sets of a vector space. Let S equals V sub 1, V sub 2 all the way through V sub K be a subset of a vector space V. The set S is a spanning set of V when every vector in V can be written as a linear combination of vectors in S. In such cases, it is said that S span V. For example, the set S equals 1, 0, 0, 0, 1, 0, and 0, 0, 1 spans R3 because any vector U equals U sub 1, U sub 2, U sub 3 in R3 can be written as U equals U sub 1 times 1, 0, 0 plus U sub 2 times 0, 1, 0 plus U sub 3 times 0, 0, 1. And then it will be equal to U sub 1, U sub 2, and U sub 3. Another, the set S equals 1x x squared spans P2 because any polynomial function P of x equals a plus bx plus cx squared in P2 can be written as P of x equals a times 1 plus b times 1 plus c times x squared. And then it will be equal to a plus bx plus cx squared. Thus, the spanning sets in this example are called standard spanning sets of R3 and P2 respectively. Another example, a spanning set of R3. Show that the set S equals 1, 2, 3, 0, 1, 2, and negative 2, 0, 1 spans R3. Solution. Let U equals U sub 1, U sub 2, U sub 3 be any vector in R3. Need to find the scalars C sub 1, C sub 2, and C sub 3 such that U sub 1, U sub 2, and U sub 3 equals C sub 1 times 1, 2, and 3 plus C sub 2 times 0, 1, and 2 plus C sub 3 times negative 2, 0, 1, and then distribute, then proceed to vector addition. Then it yields C sub 1 minus 2C sub 3 comma 2C sub 1 plus C sub 2 comma 3C sub 1 plus 2C sub 2 plus C sub 3. And then this vector equation produces the system C sub 1 minus 2C sub 3 equals U sub 1, the first component. 2C sub 1 plus C sub 2 equals U sub 2, the second component. 3C sub 1 plus 2C sub 2 plus C sub 3 equals U sub 3, the third component. The coefficient matrix of this system has a non-zero determinant, and we need to verify that it is equal to negative 1. And it follows from the list of equivalent conditions in the previous lesson that the system has a unique solution. So, any vector in R3 can be written as a linear combination of vectors in S, and we can conclude that the set S spans R3. Next example, if possible, write the vector W equals 1, 2, and negative 2 as a linear combination of vectors in the set S. Solution. A set that does not span R3. Following the procedure from the previous example, the result of the system is C sub 1 minus C sub 3 equals 1, 2C sub 1 plus C sub 2 equals negative 2, 3C sub 1 plus 2C sub 2 plus C sub 3 equals 2. Sa previous nga example, gigamit kay katong U sub 1, U sub 2, and U sub 3. While diri sa kani siya nga example, na siya gikuan nga vector vector W which is 1, 2, and negative 2. So, the augmented matrix of this system row reduces to 1, 0, negative 1, 0, 0, 1, 2, 0, and 0, 0, 0, 1. Sa third row, ma-conclude nato nga ang system of equation is inconsistent, which means that there is no solution. Consequently, W cannot be written as a linear combination of V sub 1, V sub 2, and V sub 3. So now, let's proceed to the definition of the span of set. If S equals V sub 1, V sub 2 all the way through V sub k is a set of vectors in a vector space V, then the span S is the set of all linear combinations of the vectors in S. Span of S equals C sub 1 V sub 1 plus C sub 2 V sub 2 plus all the way through C sub k V sub k, where C sub 1, C sub 2 all the way through C sub k are real numbers. The span of S is denoted by span of S or span V sub 1, V sub 2 all the way through V sub k. When span of S equals V, it is said that V is spanned by V sub 1, V sub 2 all the way through V sub k, that S spans V. Another, Theorem 4.7. Span of S is a subspace of V. If S equals V sub 1, V sub 2 all the way through V sub k is a set of vectors in a space V, then span of S is a subspace of V. Moreover, span of S is the smallest subspace of V that contains S, in the sense that every other subspace V that contains S must contain span of S. So, kani siya no, nga theorem kay ma-discuss ni siya for sa next lesson. Now, the definition of linear dependence and linear independence. A set of vectors S equals V sub 1, V sub 2 all the way to V sub k in a vector V is linearly independent when the vector equation C sub 1 V sub 1 plus C sub 2 V sub 2 plus all the way to C sub k V sub k is equal to 0 and has only the trivial solution C sub 1 equals 0, C sub 2 equals 0, all the way to C sub k equals 0. But if there are also non-trivial solutions, then S is linearly dependent. Example for that: determine whether the set of vectors in R3 is linearly independent or dependent. S equals V sub 1, V sub 2, V sub 3 equals 1, 2, and 3, which is the V sub 1, 0, 1, and 2, which is the V sub 2, and negative 2, 0, 1, which is the V sub 3. Solution. To test for linear independence or dependence, form the vector equation C sub 1 V sub 1 plus C sub 2 V sub 2 plus C sub 3 V sub 3 equals to 0. Equate na siya into 0. If the only solution of this equation is C sub 1 equals C sub 2 equals C sub 3 equals 0, then the set S is linearly independent. Otherwise, S is linearly dependent. So, expanding the equation, we have C sub 1 times 1, 2, and 3, which is the V sub 1, plus C sub 2 times 0, 1, and 2, which is the V sub 2, plus C sub 3 times negative 2, 0, 1, which is the V sub 3, is equal to 0, 0, and 0. So, distribute vector addition. It yields C sub 1 minus 2 C sub 3, 2 C sub 1 plus C sub 2, 3 C sub 1 plus 2 C sub 2 plus C sub 3 equal to 0, 0, 0. This yields the homogeneous system of linear equations in C sub 1, C sub 2, and C sub 3. So, C sub 1 minus 2 C sub 3 equals 0, first component, 2C sub 1 plus C sub 2 equals 0, second component, and 3C sub 1 plus 2C sub 2 plus C sub 3 equal to 0, which is the third component. And then, using Gauss-Jordan elimination, the augmented matrix of the system reduces, as shown the screen, 1, 2, 3, 0, 1, 2, negative 2, 0, 1, 0, 0, 0, be reduced to 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, and 0, 0, 0. If makita niyo sa right side or the last column, 0 siya tanan. So, this implies that the only solution is the trivial solution, C sub 1 equals C sub 2 equals C sub 3 equals 0. So, S is linearly independent. Another example, determine whether the set of vectors in P2 is linearly independent or linearly dependent. S equals 1 plus x minus 2x squared, comma 2 plus 5x minus x squared, comma plus or rather x plus x squared. Solution, expanding the equation C sub 1 V sub 1 plus C sub 2 V sub 2 plus C sub 3 V sub 3 equals 0. It produces C sub 1 times 1 plus x minus 2x squared, which is the V sub 1, plus C sub 2 times 2 plus 5x minus x squared, which is the V sub 2, plus C sub 3 times x plus x squared, which is the V sub 3, will be equal to 0 plus 0x plus 0x squared. And then distribute C sub 1 plus 2C sub 2 plus C sub 1 plus 5C sub 2 plus C sub 3 times x plus negative 2C sub 1 minus C sub 2 plus C sub 3 times x squared equal to 0 plus 0x plus 0x squared. And then we will equate the corresponding coefficients of powers of x. It will yield the homogeneous system of linear equations in C sub 1, C sub 2, and C sub 3. C sub 1 plus 2 C sub 2 equals 0. C sub 1 plus 5 C sub 2 plus C sub 3 equals 0. Negative 2 C sub 1 minus C sub 2 plus C sub 3 equals 0. By using Gaussian elimination as shown in the screen, the augmented matrix of this system, no? Okay, reduce siya into 1 to 0, 0, 0, 1, 1/3, 0, and the last row is 0 na siya tanan. Now, this implies that the system has infinitely many solutions. So, the system must have non-trivial solutions. And we can conclude na the set S is linearly dependent. Now, one trivial solution is C sub 1 equals 2, C sub 2 equals 1, and C sub 3 equals 3, which yields the non-trivial linear combination 2 times 1 plus x minus 2x squared plus negative 1 times 2 plus 5x minus x squared plus 3 times x plus x squared equal to 0. So this ends our lesson 3. Let's now proceed to the next reporter for the lesson 4. Thank you.